Alright guys, we'll look at a couple more examples. So now we're going to look at a couple examples that involve processes of decay. So in those instances, the only difference will be the value of k will be a negative number. Okay, that's it. And for, future values of the function, they will be decreasing, okay, because it'll be a decreasing exponential function. But anyway, let's look at this example 3 here. Zoom in a bit. It says the amount of advertising revenue in the U.S. newspapers has declined continually since 2006. In 2006, the advertising revenue was $49.3 billion, and in 2013, that amount had decreased to $20.7 billion. Okay, so in a difference of 7 years, the revenue has decreased by about $28 billion. And it says, assuming that the amount of newspaper advertising revenue decreased according to the exponential decay model, okay, that we were using above. Write it again here real quick. We want to, part A, find the value of k and write an exponential function that describes the advertising revenue after time t in years, where t is the number of years after 2006. Okay. So one thing you'll notice about this problem is that they don't give us k, and in the previous two problems they did. However, they do give us enough information to find k. They give us basically the function evaluated at 2 different points in time. The amount associated with 2006, which would be when time is 0, and then the amount associated with the function evaluated in 2013, which is 7 years later. So in other words, when t is 7. Okay. So for part A, before we can write that function, we first need to figure out what k is. Well, the difference between those 2 years, 2013 and 2006, that's a difference of 7. Okay, so t is 7. And we can come up here and use this formula. Now, technically, the way you would do this is you would say, you would use this template right here with the future value as your function value, and the value in 2006 is your initial value, and you would plug 7 in for t, and you would solve this equation for k. So it would be another exponential equation. You'd solve it the same way we did that very first example. Dividing both sides by p0, taking the ln of both sides, and then dividing both sides by, in this case, it would be t. But that process is condensed in this formula. Or, whoa, wait a minute. No, this is for doubling time. You can only use this formula if, this is not going to work actually. We're going to have to solve it the way I was explaining. Okay. Alright, so the future value of this function is the 20.7 billion, because remember, this is decreasing. 20.7 billion is equal to the initial revenue, which is 49.3 times e to the k. Well, we don't know what k is, but we do know what t is. Okay, t is 7. Or you could even write this as 7k if you want. I think that's what I'll do. Well, no, I guess not. K times 7. Okay. Well, again, first thing I'm going to do is divide both sides by 49.3. Now this over here on the left, I'm just going to look at it like it's a number. I'm going to do the actual division at the very end. Okay. And then this is equal to e to the, now I'll write it as 7k, e to the 7k power. And now I'm going to take the natural log of both sides. Okay. Is equal to the natural log of e to the 7k. Again, using that power rule, we can pull that 7k in front. The natural log of e is going to disappear. Okay. And so I'll be left with just dividing both sides by 7. So you could still derive a formula for this if you wanted to. But k will be roughly equal to, I'm going to plug all this into the calculator. The natural log of 20.7 divided by 49.3. Close those parentheses and then divide all that by 7. Okay, now this is a decimal and it's negative. Okay, so it's negative 0. You want to carry this out several decimal places. I'm going to carry it out to 4 decimal places. So this 7 would bump that 9 to a 10, which would make this 39 go to a 40. So this would be 0.1240. 1240. Okay. So that's our value of k. That's our growth, well, rate of decay in this case because it's negative. So now if I want to express my formula, or excuse me, write this as a function of time, the initial revenue in 2006 is 20.7 billion times e to the, now we actually have a value for k. Okay, and I'll leave that 0 off, and then this will be t. Okay, so that is our function. So that's what we're going to be using to answer the rest of these questions. So part B says, estimate the advertising revenue in 2008 and 2012. Well, 2008 would be 2 years from 2016. So basically t would have a value of 2. In 2012, that would be 6 years from 2006, so t would have a value of 6. So all we're doing now is we're going to use that function that we found. And we're going to evaluate it for those 2 different values of t. Okay, so in other words, we want to find p of 2. That corresponds to 2008. This first one, again, I'll just write everything out to show you. But 2012, that corresponds to 6 years. Okay. Put a 2 in there. All right. So let's try this. So I'll type in 20.7 times e to the power of negative 0.124 times 2. And hit enter. And wait a minute here. You know what? I used the wrong number in all these calculations. I have my numbers backwards. Well, let's see. Well, no, the first part is good. Okay, it's just the initial revenue is not 20.7 billion. It's 49.3 billion. So that's where I made a mistake. Everything else here is correct. Okay. Ooh, something didn't look right. Sorry about that, guys. 49.3. That's the initial revenue. So that's what I need to have right here. Because it's decreasing. Okay. Alright, so you would just type the same thing in, but just don't use 20.7. In fact, what I'm going to do is I'm going to say second entry, and I'm just going to replace that initial value, or initial amount, with 49.3. There we go. Okay. Now I'm going to hit enter. Okay, this looks more like it. So in 2008, the revenue will have fallen to, if we round to the nearest tenth of a billion, this would be 38.5. So we'll say this is approximately equal to 38.5. And we need to keep the word billion on there. I'm going to put the dollar sign too, because we're talking about revenue. And then I'll do the same thing whenever t is 6, or for 6 years. Second entry. And I'll replace that t, or that 2 with a 6. And hit enter. Now it's going to be roughly 23.4 billion. Approximately equal to 23.4 billion dollars. Okay. Alright, so hopefully you can see these problems are just really the same. They're just permutations of the same type of problem. The only difference here is that initially k wasn't given to us. We had to find it. Okay. Alright, well that answers part B. What about part C? It says at this decay rate, when will the advertising revenue be 16 billion? Alright, well they're giving us a future value. Okay. We already know the decay rate, so we need to solve for t. Okay, so it's that same. So for C, we're going to set our function equal to this future value. Okay, 16 billion. So 16 billion is equal to our function. So again, we're going to get another exponential equation. And we're going to solve it for t this time. That'll tell us how long it takes the revenue to fall to 16 billion. Okay, from the year 2006. You have to keep that in mind. All right, well, I'm going to solve this the same way. I'm going to divide both sides by that initial value. Okay, and again, you know, I'm just going to treat this as one value here. I'll do my dividing at the end. These will divide out. It'll become e to the negative 0.124 times t is equal to 16 over 49.3. And we'll take the natural log of both sides. Okay. That'll move this exponent out in front, so we'll have negative 0.124 times t times the natural log of e, which will turn into 1, or go away. And that will be equal to the natural log of that quotient, 16 divided by 49.3. And then the last step here will be divide both sides by k. And so I'll show that in the calculator. So t will be approximately equal to, actually I'll rewrite it over here. Natural log of 16 divided by 49.3 divided by k, which is negative 0.124. Okay. So this will tell us alright, so the natural log of 16 divided by 49.3, close those parentheses, and then divide that by k, which is a negative 0.124. Alright, so this is approximately to the nearest year, or excuse, well, yeah, let's say to the nearest tenth of a year. This would be 9.1. 9.1 years. Again, remember, if it asks when will the revenue have fallen to $16 billion, we're counting from 2006. So, in other words, 2006 plus roughly 9 years would be 2015. So this is actually the answer to your question. So you have to be careful here. You've got to keep in mind that this function models the decline in revenue from 2006. Okay. So this would be 9 years from 2006. So in other words, 2015. That's when we could expect the advertising revenue to have fallen to roughly $16 billion. All right. Okay. Well, I've got one more for you. It's not quite as long. It doesn't have a part A, B, and C. But let's read it. It's another problem in which we're going to apply exponential decay. It says the number of farms in a certain state has declined continually since 1950. All right, so this is our starting date right here. And in 1950, there were 92,758 farms. So this is the initial value. And in 1995, so 45 years later, the numbers decreased to 20,827 farms. So over this 45-year period, assuming the number of farms decreased according to that exponential model that we've been using, find the value of k and write an exponential function that describes the number of farms after time t in years, where t is the number of years since 1950. So this is this same part A done over again, okay? All right, so the future value, or the future number of farms, is the 20,827, and that will equal, remember your function template here, okay? And that will equal the initial value, or the initial number of farms, in this case, which is 92,758, times e to the power of k. Well, we don't know what k is. We do know what t is. From 1950 to 1995, that's an interval of 45 years. Okay, 1995 minus 1950, that's a period of 45 years. So we know the value of t. Okay. So we're going to solve this the same way. We start out by dividing both sides by that initial number of farms. Okay, so we divide out, we're left with e. Now I'll turn those two factors around. Again, I'll treat this like it's just one number here, because I want to do my dividing at the very end. And then I'll take the natural log of both sides. Natural log of e to 45k, so the power rule is going to move that 45k out in front. And then you can not even write the ln of e if you want, okay? Because you know it's going to turn into 1. 2,758. Okay, and then we'll divide both sides by 45. And so k will be approximately equal to, and I'll plug all this into my calculator. Natural log of 20,827. And just pay attention to your numbers, guys. It's easy to make a mistake or typo or something like that. I could be even working on one as we speak. Alright, but anyway, I come up with this value, okay? I'm going to round it to 4 decimal places again, so this will be negative 0.0332. Okay. Now, if they ever asked you to explicitly state the value of k as a percentage, you would multiply by 100, so this would be roughly 3.32%, okay, or negative. That would be the rate of decay. If they just ask you for the rate of decay as a percentage, you just put 3.32, because the word decay implies that it's a negative. Okay, so you wouldn't repeat the negative. But in any case, now to write this as a function of t, the initial number of farms is 92,758 times e. We now know the value of k as a decimal, and t. Okay, and so then that would be our function that models the decline of the number of farms in this particular state as a function of time starting from 1950. Okay. Alright, well hopefully I've worked enough of these for you so that you'll be able to finish this section, guys. And that does it for the lecture material. Okay. So all you'll have left is your module test 4. You'll have a review for the final and then the final exam. So I hope you've learned something in this case, guys. I've tried to show you how we can use functions in real life to model different behavior, how functions can be useful to us. And just having had that or been exposed to that, how that can be helpful to you, okay, as a person in the real world, okay. So anyway, I'll talk to you guys later. Let me know if you need anything.